My name is Pradeep Kumar. I am the IEEE chair for the Communication Society for Oregon. And, with me is Russ Mikovich, who is the secretary, waving his hand, and Raf, who is the vice chair. We are, one of the 15 chapters local to Portland. And the same Portland chapter has been around for a good 30 years, maybe. Yeah. So with that, I will hand over to our moderator, who will introduce the speaker.
All right. So, Pradeep, should I go?
Yeah, go ahead.
Okay. All right. I'm Rath Vanithambi. So I'm going to, first of all, Happy New Year. It's happy to see everybody, a lot of people coming back for the distinguished lecture series. So today we are going to have Dr. Liangping Ma. He's a distinguished lecturer, Communication Society distinguished lecturer, and he is currently with Qualcomm. He's a senior staff engineer with Qualcomm, and he's working on 3GPP, 5G, NR multimedia systems. And prior to Qualcomm, he was with InterDigital for about 10 years, where he was working on 3GPP radio access network, quality of experience, and machine learning. Prior to InterDigital, he was with San Diego Research Center and Argon ST, where he was developing, he was leading the development of modem for wireless sensor networks. He has more than 100 patents, and he has been teaching a course on 5G NR at UCSD Extension since 2019. He received his Ph.D. in electrical engineering from the University of Delaware in 2004, and his BS degree in physics from Wuhan University, China in 1998. So you all heard about 5G a lot. Now today we are going to get a lot more information to understand what is 5G NR. So with no further ado, let's welcome Dr. Liangping Ma.
Okay, so yes, thank you, Pradeep, and also Ross for organizing this event. I think this is a very special time, but we are able to take advantage of the convenience of online format. I think it's really great, both for myself, I think for many of the attendees. Good evening, everyone. If you are on the East Coast. Okay, so let me.
Sorry to interrupt, Liangping. Okay, yeah, presentation mode would be good. That's great. One other thing I forgot to ask: do you mind we interrupt you for question in an interactive fashion, or do you want us to wait till the end for questions?
So maybe I can go over the presentation so that we'll have enough time to make sure we can finish the presentation before the end of the meeting, and then the remaining time we can use to handle questions. How does that sound?
Yeah, that's completely fine. Yeah. Okay.
Okay.
Thank you.
Okay, great. So today I'm going to give you an introduction of 5G NR, and my goal is to give you a bigger picture, and then I will dive into some of the important aspects of 5G NR. First, I'd like to thank my colleagues from the ESG group within Qualcomm for providing the content of this presentation. And also, as a note, this presentation focuses on release 15 for 3GPP. So there are more recent releases, release 16, and ongoing release 17. But Release 15 is the bare bone, the foundation of NR. First, I will give an overview, and then I will get into the details of several aspects, including numerologies, protocol stack, initial access, control channels, data channels, beam management, and bandwidth part. So 5G, if you look at the typical diagram, we have three major use cases. We have the enhanced mobile broadband, or eMBB, which is featured by very high data rate. And we also have a mission critical control use case, which is featured by two characteristics. The one is very high reliability, the other one is a very low latency. And there's the third use case, which is massive Internet of Things, or massive IoT. So this one is featured by very low power consumption on the UE side, also by very high device density. Here is the timeline of 5G NR specifications. The first release 15, was completed in June 2018, and it covers two deployment modes. The first one is non-standalone, or NSA. The second one is a standalone, or SA. And then we have a release 16 with additional features. And the current release is release 17. In release 17, more verticals are added just to enrich the scope of 5G NR. For instance, the satellites are being considered, so that can greatly significantly expand the scope of 5G NR. This one shows some of the key technologies within 5G NR. The first one is on the waveform. The waveform is OFDM based, but it's different from the OFDM, the waveform used in LTE, in the sense that the OFDM is more scalable in NR. You could have different subcarrier spacings to address very diverse spectrum and deployment scenarios. Also, the second one is the numerology, the slot-based numerology, which is making NR very flexible. Also, it enables some of the very low latency operation for supporting ultra reliable and low latency applications. There's a significant difference between 5G NR and 4G LTE in the sense of the, in terms of the spectrum. 5G NR uses the millimeter wave spectrum, which gives a much more bandwidth for communication, and that can significantly increase the capacity. And there's also the use of a very large number of antennas, which enables massive MIMO, which can significantly increase the system throughput. And in 5G NR, because of the use of very high frequency, the millimeter wave spectrum, the path loss can be large. To counter the large path loss, the base station can form very narrow beams, very high gain beams. However, this has the drawback that each beam can only cover a small portion of the cell. So it's important to, so the solution in NR is to use the concept of beam sweeping to sweep the beam across the different angles to have a wider coverage. Also, NR uses a new channel coding schemes. For the data channel, NR uses the low density parity checker code, or LDPC, and for the control channel, it uses the polar code. And the reason for using LDPC is to have achieve very high throughput. And the reason for using the polar code is to have very high reliability. So now let's look at the scalable numerologies. For NR, it supports the not only the 15 kilohertz subcarrier spacing, which is supported in LTE, and also supports other subcarrier spacings, 30, 60, 120, and 240 kilohertz. So this can have the benefit of reduced latency. Also, using larger subcarrier spacing can increase the robustness to a certain channel impairment, such as phase noise and Doppler offset. And for the millimeter wave, the subcarrier spacing, it also supports several subcarrier spacing, and the maximum is 240 kilohertz. Now let's look at the channel bandwidth. In release 15, a channel can consist of a maximum of 275 PRBs, and because of the diverse values that can be used on the subcarrier spacing, so this translates into a very wider range of channel bandwidth that can support a very diverse range of applications and UE devices. For instance, if you for the highest for the subcarrier spacing of 120 kilohertz, the channel bandwidth can be as wide as 400 megahertz. There's also these self-contained slots. They basically the HARQ, the HRQ acknowledgement can be sent within the same slot where the data is transmitted. So the first diagram shows this. That's the first use case. And this can significantly reduce the latency. The second use case, the uplink data transmission and the downlink grant can be, they can occur in the same slot. So there, as I mentioned earlier, there are two modes, the 5G standalone mode and the non-standalone mode, NSA. The by standalone, it means the UE will communicate with the 5G base station only, and the core network is also 5G. By non-standalone, the UE will simultaneously connect to the LTE base station and the 5G NR base station. And also for the non-standalone mode, the core network will be the 4G core network, which is the EPC. The motivation of having this non-standalone mode is to leverage the existing LTE and the existing 4G core network. So if you look at the protocol stack, the 5G protocol stack is the same as that of 4G, except that 5G also has this additional sublayer, which is called SDAP, which stands for Service Data Adaptation Protocol. So the purpose of this is to assist in quality of service provisioning. This SDAP, when it receives a quality of service flow, it will map the quality of service flow to data radio barriers. And then the data radio barriers will be serviced by the RAN. And also SDAP can do the mapping for the reverse link, meaning mapping data radio barriers back to the quality of service flows. So a little bit more details on SDAP. The SDAP, besides the mapping, so you see the green diagram, that's for the downlink. The quality of service flow is mapped to data radio barrier, and the blue portion of the diagram, that's for the uplink. Data radio barriers are mapped back to quality of service flows. So there's one difference between 4G and 5G in provisioning quality of service. 4G you use PDN connection and EPS bearer. In 5G we use PDU session, and each PDU session may consist of multiple quality of service flows. And this could have the benefit of providing unequal packet protection or differentiated service between two endpoints, which has been pretty difficult to do with LTE and 4G. So this one is on the initial access, which is, so we first look at the downlink signal that enables initial access. This is the SSB, which is a connection of several transmissions, including the PSS, primary synchronization signal, SSS, which stands for secondary synchronization signal, and then a broadcast channel, PBCH. And they together form a relative fixed structure, and they occupy 4 consecutive OFDM symbols. And if you look at the diagram, this is PSS. It occupies 120 subcarriers in the frequency domain, and there are some subcarriers are blank. And then we have the SSS. Also, there are few blank subcarriers. So the purpose of having blank subcarriers is to help with detecting these signals and avoid interference due to frequency offset. And also we have this PBCH. So the gray portion, these together are the PBCH. And the PBCH carries the critical system information, such as the MIB or master information block, and plus some other information. The SSB, that's an individual SSB, multiple SSBs, and they are organized into SSB burst, and the burst can appear periodically. And this diagram shows that in this case we have this one SSB burst set has 4 SSBs, and this can the transmission of SSB burst set can be periodic, so that the UE can have multiple chances of detecting the SSB. And the SSBs, each SSB is transmitted into using a particular beam. So by doing this, the SSBs together, they can have a wider coverage. So let's take a look at the PBCH, the payload. Each SSB block carries a PBCH payload. This payload can be is self-decodable, and the repetition, the periodic transmission of SSB bursts, you can identify the repeated SSBs. For instance, over this 20 millisecond time interval, and the payload, the master information, the MIB within the SSBs for 4 consecutive SSB repetitions in a span of 80 milliseconds are the same, are identical. So this can be leveraged to have a better decoding of the MIB information, the master information block payload. And this is very similar to LTE. So there's a very important aspect, which is about the association between the beams and the random access resource. A very important question for the base station to know is that which SSB works best for a particular UE. So how does the system resolve this this issue? So basically, the UE will listen to the SSBs, and it will pick the best SSB, which can be the one with the highest RSRP value, the strongest signal, the receiver signal value. And there's a mapping for the random access resource and SSBs. So the UE will choose the random access resource, the right resource corresponding to a particular SSB, a particular beam. And by receiving the random access preamble in the right resource, the base station knows which beam works best for the UE, and the base station later on can use the same beam to transmit data to the UE. So this is further details. Let's say we have 4 beams, and they are mapped to different random access occasions. So random access occasion is another name for the random access resource. And so this mapping enables the signaling, the implicit signaling of the best received beam at the UE to the base station. So now let's take a look at the control channel. The control channel in 5G is different from in 4G. So first, there's this notion of a core set, control resource set. Control resource set consists of a few OFDM symbols in the time domain, and also a number of multiple of chunks of resources. Each chunk has 6 PRBs. And however, the starting OFDM symbol is not defined, so you can think of a core set as a chunk of resource in the time frequency grid, resource grid. So this is one part of the control channel. So this core set doesn't fully determine the location of the resources for PD6H, the control channel to use. And then there's search space. Together with the core set, they fully determine the candidates of the control channel in the time frequency resource grid. And there's a special core set that is the one which is often referred to as core set 0, which is the core set that will contain PD6H, and that PD6H will schedule resources for dynamic transmission, and that transmission carries important system information, which is often called SIB1 information, System Information Block 1. That's also sometimes called Remaining Minimum System Information, or RAMSI. For the UE first receive the SSB by checking on the sync raster. So it will try to detect SSB And then the SSB will indicate the location of core size 0. So the location could be several. There could be several cases. For instance, this is a time division multiplexed with the SSB, and also this one, and the multiplexing could be in the frequency domain, and this is another situation with the same time interval. So special case of Python 2. So by so UE first decode SSB and then go to core size 0. Core size 0 will have the scheduling information for the PDSSH, and the PDSSH carries the Ramsey information. And once the UE finishes decoding the PDSSH, then it will get the system information, more system information, and receive the configuration, and then it can start random access. So now let's take a look at the data channel processing. This is applicable to both the downlink transmission and uplink transmission. First, given a transponder block, so that's basically could be a very large packet, a very large chunk of data. The CRC is calculated and attached to this transponder block. And then in NR, the channel code for the data channels is the LDPC code. There are two codes are encoding structures are defined. So each one corresponding to the so-called base graph. And the selection of the base graph is based on the transponder block size and the coding rate. Roughly speaking, for lower coding rate and shorter block size, transponder block size, base graph 2 is selected. Otherwise, base graph 1 is selected. Then to limit the channel coding complexity, this transponder block plus the CRC bits are segmented into code blocks. And the code blocks are then individually channel encoded using LTPC. After that, bit matching will be done, and the resulting code blocks will be concatenated into a larger one, and that larger one will go through scrambling. The purpose of scrambling is to randomize the interference, and then there's the familiar step for modulation and mapped to different layers, and there could be pre-coding done after the layer mapping, and then there's the outputs are sent to different antenna ports, and there could be additional frequency interleaving by using this VRB virtual resource block mapping, the virtual resource block and the physical resource block mapping. So that's the procedure for the data channel transmission. 5G can have a very large number of antennas, especially on the base station. So that enables a massive MIMO. For massive MIMO, you can get very narrow high gain beams. But again, as I mentioned earlier, this also has its disadvantage because each narrow beam can only cover a very small portion of a cell. To make sure the coverage is broad enough, we can do a beam sweeping so that basically you just change the direction of the beam so that each UE has a good chance to be serviced by one of these beams. Now let's look at the MIMO transmission. In the downlink, 5G only supports non-codebook based transmission. So basically, the reference signal and the data go through the same precoding, and the precoding and the physical channel together can be estimated by the UE using the reference signal. So this is non-codebook based because from the UE's perspective, it doesn't need to know what precoding matrix is applied to the downlink transmission. The effect of the precoding matrix is also estimated. The combined effect of the precoding matrix and the physical channel is estimated by the reference signal. So the reference signal here is demodulation reference signal, DMRS. For the uplink, NR supports both codebook-based transmission and non-codebook-based transmission. So instead of going through the text, I'm just going through one example here. So in here, we have, so this UE first transmits uplink reference signal. So in this particular case, this UE may have two antenna panels. So UE can use one reference signal for each of the antenna panels. And within each antenna panel, there may be multiple antenna ports. And the UE uses just one reference signal resource, which is called SRS resource, and use one sequence, SRS sequence, but the sequence will be cyclically shifted to maintain the orthogonality between these sequences, the original sequence and the shifted sequences, because the sequences are Z of 2 sequences. So if we shift the sequence, then the shifted one is orthogonal to the original sequence. And the base station will measure on the SRS resources and then determines which antenna panel is better, and it will signal the indicator of the SRS resource, which is called SRI. So in this case, SRI2 is signaled. Also, it will indicate the rank indicator, how many layers the UE can transmit in the uplink. Also, the base station will signal the precoding matrix index called TPMI for the uplink transmission. And then using the information, the UE will select the antenna panel corresponding to SRS2, and then use the precoder corresponding to the TPMI. In this case, it uses the precoder for a 2-layer uplink transmission. So this is a codebook based because the UE uses a precoder matrix drawn from a codebook that is indicated by this TPMI. So there's also non-codebook based transmission. So in this case, again, let's look at this example. First, the base station transmits a downlink reference signal, for instance, CSI-RS, and the UE will estimate the downlink channel, and then use the estimate as the channel estimator for the uplink channel. So this is based on the assumption of a channel reciprocity, which is valid most of the time for TDD. And then the UE will pre-code reference signals in the uplink transmission, and the base station can will receive and determine which of the encoding weight vectors can be used, and then the signals, this SRI, indicate back to the UE, and the UE will use that information to adjust the pre-code for the uplink transmission. So now let's look at beam switching. In the previous when we talk about initial access, we have the UE receiving the SSB transmission. So these sometimes are called P1 in beam management. So that's the first phase to find the correct base station transmitter beam and correct the best UE receive beam. So this one, this diagram, if the base station, the Geno B, can transmit on different using different reference signals in different beams, and then the UE can measure the SSBs or CSRS based beams, and then it can send back the measurement, and the base station can decide which beam is better for the UE. So in this case, initially beam 1 is better, and then after some time, the UE's measurement indicates beam 2 is better, then the base station can change the beam to beam 2, switch to beam 2. So you can imagine when you have, after you send the SSB beams, then the base station can form multiple narrow beams, such as the beam 1, beam 2 here, and then the UE can select narrow beam, in this case beam 2. So by doing this, the base station has a sharper beam toward the UE. So then that's on the base station side, and then you may ask, what about the UE? The UE could have different receive beams, but which one is best for communicating with that particular base station? So this can be done by letting the base station repeating beam formula transmissions. In this case, the base station can form beam 1 and repeats the beam 1 at different times. And then the UE can use try different receive beams, and then it can pick the best receive beam. So this step is called P3 in some literature, and early stage of the 3GPP standards activities. So now there's also a concept which doesn't exist in LTE, which is a bandwidth apart. A bandwidth apart is a set of contiguous PRBs in a single carrier. And it also has some associated properties, such as the subcarrier spacing, the cyclic prefix, the control channel configuration, data channel configuration. And it's a very big concept. And the motivation of using bandwidth aparts is to give the flexibility to the devices. For instance, a base station may operate in a very wide bandwidth, but some of the devices, due to power consumption concern, may want to operate in a very narrow bandwidth. So by using bandwidth apart, that can allow certain devices to operate in very narrow bandwidth, and other devices simultaneously can operate in very wide bandwidth, and they all communicate with the base station at the same time. So this diagram gives two examples of a bandwidth parts, bandwidth part 1, bandwidth part 2. You can see that the bandwidth of the bandwidth parts can be very different, and also the duration can be different, and can be activated, deactivated dynamically, or through the control from the base station. You see that with bandwidth part 1, there are some core sets, so this will carry the downlink control channels. So there are different types of bandwidth parts. For instance, we have the initial bandwidth part. That's where the initial access happens. The UE will use the initial bandwidth part for both the initial uplink bandwidth part, the downlink bandwidth part for random access. Also, there's a default bandwidth part, which is the bandwidth part for the UE to fall back on when the UE is inactive in a different bandwidth part for an extended period of time beyond the timer. And there's also optionally you can configure the network configure the first active bandwidth part. So that's the first bandwidth part that UE can use with the configuration from the RRC message. It's different from the initial bandwidth part. So let's look at when the bandwidth parts are used, different types of bandwidth parts. So we have the UE, we have the Geno B. The initial access, such as acquiring SSB, getting the Ramsey information. So these occur pretty much on the initial bandwidth part. Then the random access procedure will take place on the initial bandwidth part. After that, after the random access, the UE will receive RRC configuration. So the configuration may contain a new bandwidth part, dedicated bandwidth part configuration. So the UE can use that new bandwidth part for future communication. Okay, so that's my presentation. And so that's a part of, yeah, also I'm, as Rath just mentioned, I'm also teaching a course at the UCSD Extension. The title of the course is the Fundamentals of 5G NR, and it gives more details. And it's designed to be very flexible to accommodate a different, wider range of needs. And some people, some students, they needed to learn this for job interviews, and some just want to have relatively high level understanding of 5G. So this is the flexible assignments and the course material so far served the students pretty well. So if you're interested, you can. So incidentally, today is the first day of the new quarter of this course. So a good date. Rath and Pradeep and Ross have chosen. Okay, so that's my presentation. Then I'm open for questions. We have so far we have spent 50 minutes.
Thank you, Liang Ping, for your very detailed review of the 5GNR release 15. A lot of information. Let's see, folks, if you want to ask questions, please unmute and ask the questions.
Hi, Liangping. I have a question regarding the beam sweeping. So during the beam sweep, the beams themselves, what is the typical beam width that we would experience?
That's a good question. The beam width depends on how many antennas you have. So the more antennas you have, chances are you can form narrow beams. So in the and also it depends on also the number of antennas you can have on the base station. Also depends on the frequency. For instance, in millimeter wave, you have because of the wavelength is much shorter, then you could you have the physical space to put more antennas there, so you can form narrow beams. So the standards doesn't specify how narrow the beams will be, especially when you talk. The specification talks about antenna ports. So each antenna port is a logical antenna. In reality, it may correspond to many physical antenna elements, so they can do pretty narrow analog beamforming. So this is so I guess the answer to your question is this: there's a very wide range of beam width for the beams that can be formed by ENA.
Okay, is there a general range of beam width degrees that is documented, or is it going to be variable depending on the antennas?
Again, I think I can give you a range. In the worst case, the base station doesn't do any beam forming, so that's the same as LTE. So then you have 120-degree beam.
Mm-hmm.
And the narrow beams, if you go with 256 antennas, that can be very narrow. I don't know how narrow it will be. As I said, you have this antenna ports, right? So each antenna port may be the result of may contain many physical antenna elements. So it depending on how many antenna elements you have, that can the actual beam width can vary in a very large range.
Okay, thank you.
I have a related question on the beam switching. So in that, does the base station has the full control of what should be the beam to be given to that UE, or does the UE has any additional say other than just sending the measurements?
That's a good question. So the procedure is the UE will take measurements on different beams. Each beam has its own reference signal, so the UE can identify. And the decision, the decision is the decision is made by the base station. So the UE really doesn't have much say on that, unless the UE want to. But when it comes to implementation, the UE, I think is almost fully controlled by the base station. So, but the UE side, when it takes the measurements, the accuracy of the measurements, that will affect the decision to be made by the base station. So the UE does have some influence on the decision by the base station. But on paper is determined by the base station.
I see. Okay, thank you. One more related question on that one. How exactly the downlink receive beam is chosen? You showed a slide, how exactly that is chosen. Does the who has the control here? Complete UE or both your G0B and the UE?
This is a good question. For the receive beam, the decision is made by the UE, and the UE doesn't need to let the base station know. And this is a local decision making, and so fully controlled by the UE.
Okay, great. Thank you.
So I have a follow-up question on that. So regarding the receive beams and the switching, so beam repetitions and switching, how is every beam being repeated every time? and how is the frequency being selected?
Yes, every beam is repeated a number of times. So there's a configuration. So the UE knows how many times the beam will be repeated and at what time the beams will be repeated. And your second part of the question, I didn't quite follow. Could you repeat?
Yes. So I understand like there is the UE will try to like receive the beams, and then there will be the communication happening between the base station and the UE. So that means like every time the beam is repeated, like beam one to when the beam switching happens, all the beams will be repeated for X number of times, and that depends on the UE, correct?
You mean what depends on the UE? Could you?
So will the UV tell the base station like how many times the repetition has to be there, or will the base station decide?
That's configured by the base station. This is
Okay.
in release 15. I guess in release maybe 17. So there at least some discussion about the UE may make a recommendation on how many times the repetition, how many repetitions are needed to be done based on the UE's certain characteristics.
Okay, got it. Thank you.
Well, this is Clark from Intel. I have a question. So in the low band, many countries at the low band, like 3.5, 2.6 gigahertz, we have IoT advanced, widely deployed. And what is the major technical advantage of 5G NR on this low band frequencies, versus LTE advanced? What's the kind of, for example, what's the spectrum efficiency improvement it can achieve, and what's the kind of additional technical enhancement it has over LTE?
Yeah, that's a good question. So LTE itself has been evolved and has been pretty sophisticated. Also supports large number of antennas, hybrid beamforming. I think you can. There are still quite some differences. For instance, the channel codes are different. So LTE use turbo code, and I use LTPC. LTPC it's easier to parallelize the processing, so it could have a higher throughput. Also for the control channel, NI uses the polar code, and that's have a much better performance than the channel code used for the LTE control channel, which is TPCC. So that's one. So that's in the error performance, and now will be better. Also, if you look at the spectrum efficiency, the 5G now is designed to have a higher spectral efficiency. For example, on the Gauda band can be, I think the efficiency is very close to 100%. For LTE, it's a little bit far away. And also, you consider flexibility. For instance, we talked about the bandwidth part. NR can support very narrow band devices, very low power devices, but for LTE, you don't have such a luxury. So I think these are some of the things I can think of right away.
Thank you.
One follow-up question on the bandwidth part. So, you talked about that the bandwidth parts are kind of, specific to UE. UE, can have smaller, bigger based on their needs and the capabilities. And these bandwidth parts are assigned for different duration. So from the base, can you tell something about how exactly the base station manage these bandwidth parts across the UEs for different duration of time?
Yes, that's a good question. So the bandwidth part, so there's so the base station, I think this is a coarse granularity scheduling problem for the base station, because the bandwidth apart, each bandwidth apart, that's the so when you allocate a bandwidth apart to a UE, basically that's the range of a constraint for future resource allocation. So all the resources you allocate to a particular UE will come from that allocated bandwidth apart. So in which, so for the UE, for the base station, it needs to decide where to carve out the frequency and to meet the demands from multiple UEs. So it's really a scheduling problem. It's the specification doesn't come to how the base station allocates bandwidth the parts to different UEs, but that leaves the implementation entirely to proprietary solutions. But I think a lot of work can be done, but this is it's going to be a lot of interesting work can be done, and also the benefit is very clear. And about the duration of each bandwidth apart, so the bandwidth apart first is allocated, and so that's the starting time of the bandwidth apart, and then the base station can change the bandwidth apart, or activate, or the base station can deactivate current bandwidth apart. For instance, if there's a very high load in the channel and some UEs quality of service is suffering, then it may configure a different bandwidth apart for some UE that doesn't have so much traffic. So, and then the base station can send a command to the UE to switch to a narrow bandwidth apart to leave more resource for other UEs. So things like this can be done.
I see. Yeah, that's a good thing. And you also mentioned like the showed a like a message diagram, the initial bandwidth part. How exactly the UE get the initial bandwidth part? Is that through RIMC or something else?
That's a very good question. I think I have a diagram. So the initial bandwidth apart, together the UE first will acquire the SSB. The SSB carries the configuration for core size 0, and core size 0 has I think we'll have a diagram on that. Yeah, so this is the SSB transmission. The UE in here there's this MIB, the payload of the PBCH MIB. MIB information, there's indication on the core size 0. So then the UE goes to core size 0. There's a core size 0 contains the PDCH, and also the search space 0. So the UE can get the information on the PDCH. The PDCH schedules a PDSSH transmission, and here there's this Ramsey information, this SIG1 information delivered by this PDSSH transmission. And in this Ramsey, there's the configuration for the initial bandwidth apart. So that's the information the UE gets. Once it gets that information, it has the knowledge on the initial uplink bandwidth apart. So then it can do send the first message in message 1 for random access.
Great, thank you. Other questions?
I have a question about the devices with the NSA capability and how handoff or handover works between the LTE and the 5G.
And that's a good question. Yes. So for NSA, the control plane is carried by LTE. So that means the RRC configuration, everything, even though RRC configuration is for the 5G, the RRC will be forwarded to the LTE base station from the 5G base station through the X2 interface, and then will be transmitted on the LTE air interface. So when you talk about handover, so you have this RSA reconfiguration, so that will go through the LTE interface. So the LTE will send a message, and then that message has a container. That container is a complete RSA configuration for NR.
Okay.
So does that answer your question?
Yes, yes, thank you.
Other questions? I have one more question. So you talked about the self-contained subframes, two cases or two options. Can you say a little bit more on what, which case is used for what scenarios and cases?
Yes, these are the two use cases. So basically, downlink transmission, uplink transmission occur that traditionally occur in different TTIs, but now they occur in the time in the same slot. So that's a more compact design in NR. So maybe we can go into a little bit of details on, let's say, the first use case. You transmit downlink data, then you need some gap for the UE to process the data and prepare for the uplink transmission. So then at the end of the slot, the UE can send the hard acknowledgement, whether it's ACK or NAC, and can also send the SRS for to enable the base station to estimate the uplink channel. So this can, if you look at the look at LTE, so typically when you receive downlink data transmission, the ACK will occur 4 time slots on 4 TTIs from the time you receive. So the delay is 4 TTIs, but here the delay is less than 1 slot. And also for 5G, a slot can be less than 1 subframe duration, 1 millisecond, which is 1 TTI in LTE. So the delay actually could be even shorter with a higher subcarrier spacing. And use case 2, you have the downlink control. So that's the grant, and then so for the push transmission, for the uplink transmission LTE, the UE first receives the grant, and then after some time, it transmits, after a few TTIs, it transmits the uplink data. But here, this uplink data can happen within the same slot. Again, we have a gap here. So this is a sub-slot turnaround time. So this is and this makes a big difference. This is especially important for UILC use case.
How about the acknowledgement for the uplink data in the case 2?
So for this one, this is uplink data transmission, and acknowledgement will come back from the base station. So the base station will use will toggle a bit. I think is a new data indicator. So if we so that indicates whether the UE needs to send a new data or old data. So new data means the previous one is successfully received, and if it's old data, that means the previous one is not successfully received, and the UE can retransmit.
I see that goes in another downlink control part of the another slot transmission.
Yes.
Not within the same. So yeah, self-contained. Even so, it is the case 2 is not completely self-contained in that sense, right?
I think it's called self-contained. The whole data transmission is may not be over yet. You're right in that sense.
Yeah.
But the self-contained, I think the reason of using that terminology is because this grant and transmission occur during
Happening
the
in
same slot.
Yeah, makes sense. Thank you. Any other questions?
Oh, thanks very much.
Nice. One, you did not say anything about the quality of service, QCI. I heard there are additional QCIs defined in 5G NR. Can you say a few words about it?
Yeah, sure. So in LTE has been, so LTE use QCI, quality of service class identifier. So each one corresponding to a set of target performance metrics, such as the delay, the packet loss rate. Or 5G, 5G use different, is something similar but with a different name called 5QI, 5G quality of service identifier. And that has similar, so the definition of 5QI is the correspondence to the actual performance metrics. The structure is similar to LTE, but it has more, for example, the packet loss rate can be 10 to the minus 8, for instance, compared to 10 to the minus 6 in LTE. So that's the way to indicate the quality of service requirements of 5QI. Yes. And then in 5G also has this quality of service flow concept. So that's between endpoint, the UE, and maybe the UE and the core network. You could so that's called UPF. So in 5G, the gateway, the packet data gateway in LTE corresponds to the UPF, user plane function, in 5G. So the connection between the UE and UPF, that's called a PDU session. We have multiple quality of service flows. Different flows may be served differently, treated differently in the 5G core network. So it's more general and more flexible than LTE.
More advanced, definitely. Yeah. Thank you. Somebody asked a question in the chat window. Would the slides would be available for the audience?
Yeah, that's a good question. I will try to check with our company because because we have I need to get a clearance before I send anything, any document to someone other than our collaborators or our colleagues. So I will check. The slide deck has been approved, but I just need to go through the security the procedure to send the email.
Okay. All right. Yeah, sure. Thank you. Any other questions from anybody, any other audience? All right. So, thank you very much, Liangping Ma. It's a very detailed presentation and Q&A that you provided. Again, thank you very much for taking the effort to help us in the Oregon Communication Society Oregon chapter to give a really good distinguished lecture talk. Thank you very much. Let's thank our DL talk speaker today. Thank you.
Thank you, Raj. Thank you, Pradeep and Ross,
Yeah.
for organizing this event. I'm really honored. If you want to know a little bit more about 5G, you can maybe you can check out the course I'm teaching at the UCSD Extension.
Okay.
So it's not just if you want to go deep, you can go deep. The students can work on channel coding. They can actually in the past few semesters, they plotted the BR curve versus a signal to noise ratio for polar codes. I think that's really exciting for the students.
Is that in a semester course that you teach?
Yeah, it's a quarter by quarter. So it's
Okay.
I think 3 quarters a year or 2 quarters a year. So that's offered twice. Today is the first day of the winter quarter. And we also have Q&A sessions, live Q&A sessions on Zoom. So I think that some of the students really liked it.
Great, nice. And you have been doing this about 2 years now, right?
Yeah, yes.
Yeah.
It's interesting to think about the questions I received from the students. Yeah, sometimes they had a thought really deep, really hard.
Nice. Great. Pradeep, do you have anything else to add?
I thank you again, Lingma, for doing this. And yeah, it was certainly a very detailed explanation of the intricacies behind 5G. And for the rest of you who had attended, thank you all for joining this evening. If you're not aware, ComSat Portland has a new website. It's called oregon.chapters.comsat.org. That is where you will see in there supposed the upcoming events, as well as slides from the previous presentations. The materials are all posted there under meeting archives. So if we get permission from Lingma on the slides, that's where it will eventually be posted. Okay, thank you all.
All right, thank you. Thanks again.
Thank you, everyone.
Thank you.
Good night. Bye.
Bye-bye.
Good night.
Thank you very much.